switch. There's some other computers.
So you need a laptop.
Let's see if our magic point actually works. Yes, that works. Switch slides on that? Or? Yes. You have to push it, right? Point. Just like that second. All right, our next speaker is Gaute Hagen from Oak Ridge, and he'll talk about recent advances in emulating coupled cluster calculations.
Thank you, Dean. It's great to be here. And also a pleasure to give a talk on recent advances in emulating coupled cluster calculations. So, of course, I'd like to first thank all the collaborators involved in this work, especially the young people who and postdocs and students here highlighted in the boldface. So this talk will present mostly work in progress. So it's very preliminary results, and it's going to be two topics I'm going to cover. First, some of you might have heard, it was at the Triumph meeting where we use now emulators and also a coupled cluster, or what we call subspace coupled cluster, for optimization of chiral Hamiltonians, where we have gone now to N3 low order with at NN level with free-body forces at next to leading order, next to leading order, which includes up to 28 low energy constants that you need to fit to a certain set of data. And the second part is much more recent. Actually, some of the results were finished yesterday. I mean, it's very preliminary. So here we've now pushed subspace coupled cluster for constrained optimization problems. In particular, we're looking at the role of octopole deformation. So now we also not only breaking angular momentum, we also break parity in order to probe what the role of octopole deformation is. And then the first application here in Neon 20, but of course, this is relevant for computations of shift moment in heavy nuclei like radium 225, for example. So starting with the point one, so we know that certain interactions work better than others. I'll give you here just some examples. You have this magic family of magic interactions that we heard about that seems, well, performs extremely well when it comes to computing binding energy and binding energy and spectra of light, medium mass, and heavy nuclei. It also turns out that if you readjust the CD parameter of the 3 nucleon force, you can also get radii quite well described. And this is shown in this paper here by collaborators where they change the CD to quite large values. They can only also get the radii quite well described as well. On the right-hand side here, I'll show you a picture from our recent publication with Song Hao, where we computed neon isotopes using this particular interactions and also a set of other delta-full interactions for the rotational spectra of neon isotopes, and Thomas will talk more about that in the next talk.
Yeah, maybe we just take a little break to move.
Yeah, that's what I was trying to do, but with the
Can you move the talking all the way up?
that's my third thing. Let's see if it
It
stays like that.
All right. I should not use pointer.
Use it. Try.
Oh, okay, it's a learning for me too. All right, so then also we have the nuclear lattice CFT calculations here by D&D and collaborators were published in Nature last year, where they fit interaction on the lattice. Say similar like it's done with the magic interactions here. They took the two-body at the N3 low and the three-body forces next to leading order. Also additional low-energy constants that enters in the 3 nucleon force, and using sophisticated tools such as history matching and fitting to certain set of nuclei here, you can see they get a quite well description of light nuclei or medium mass nuclei for the binding energy, and for the radii, they make predictions. So those were not included in the fit, and quite remarkable agreement with data. And this is the quality. I'm getting used to this pointer. This is the quality of the nuclear scattering phase shifts, and you can see that also quite well reproduced at this order. So motivated by this, we set out to see if we can do a similar kind of study here. So taking the NN force at N3LO, while taking the two-body force at next to leading order, this amounts to having 28 Lorentz constants that we need to fit to certain data, and we use high-fidelity emulators for nuclear scattering, few-body Noble calculations in the Triton and helium-4, and we also used a couple of cluster emulators for computation of oxygen-16 properties, including both the binding energy and the radius of this nucleus. So those are the the observables that we included in the optimization, and then to see how well we can optimize such an interaction here was the task we set out to address. So some details regarding cutoffs and the regulators that we use in interaction. So we use non-local regulators with particular cutoff here of 300 MeV, 94 MeV. This is because we can reuse some of the interactions that were free-body forces that we had from the MAGIC, which has the same cutoff, so we don't have to regenerate all these kind of physical forces. And we also know that this is soft enough to converge heavy nuclei. So this was kind of motivation for choosing this particular cutoff. So just to give you, again, you heard about emulators, and we base this on the eigenvector continuation method for the couple cluster case. The difference is here that we generalize this for non-Hermitian problems. So we have, in the sense that we have a non-Hermitian Hamiltonian, we have to solve for the right and a left ground state solution in order to evaluate properties other than the energy, which we then, so basically the idea, as we heard about in several talks, right? You can write your Hamiltonian in this linearized form here, where these are the Lorentz constant, for example. And you select from this domain of Lorentz constant here, parameter domain, certain snapshots or training points where you perform now a full exact couple cluster calculation, for example. And then you project a target Hamiltonian onto that subspace of training vectors. And you can then very quickly evaluate observables for any target value of the Lorentz constant here, because it just amounts to diagonalization of a very small matrix of typically size about not more than 100 by 100. So you can easily evaluate then any observables within this limited subspace here on your, for example, on your laptop. So just to show you how it works for this is couple cluster now for the ground state energy and radius of oxygen-16. The red diamonds corresponds to exact couple cluster calculations at the singles and doubles level. Where we vary one parameter at next to leading order, the singlet S contact in this range. And you can see we have two training points now, and the solid black line is the prediction for those observables as you go, as you vary the Lorentz constant here in this range here. You see here on the x-axis. So increasing the number of points, so here we go from 2 to 3, you can see that the predictive capability gets better. And 4 points, even better, and 5 points, you can see we reproduce basically the exact couple cluster calculations over this whole range of the Lorentz constant. Of course, this is only varying one parameter, but as I mentioned, with the task that we set out to solve here, it's really involved 28 Lorentz constant, and was not entirely clear to us how well the couple cluster emulator or subspace couple cluster would work such in parameter space. So we were surprised, actually, it works quite well. So this is showing you now the ground state energy on the upper left corner here the subspace couple cluster predictions versus the exact couple cluster singles, doubles with triples on the x-axis. For the binding energy, on the right-hand side, you see the predictions for the proton radius, emulated couple cluster versus the exact couple cluster calculation. And you can see this is the error of the binding energy and the radius. So you see that we are better than 1%, typically for the predictions for the binding energy, and also quite well for the point proton radius. So here we have 84. So that's in the parentheses, so it's subspace couple cluster with 84 training points or snapshots.
How do you sample them from a leading?
Yeah, we use that hypercube sampling method. So okay, so then we also made predictions for the phase shifts. So these are the quality for selected partial waves, and I would say quite well reproduced. There's maybe one partial wave that is a bit worse than the other. The BP2 channel here, and it turns out that there is a compromise between getting oxygen right and also getting this particular phase shifts partial wave correct. So then coming to predictions for binding energies from light to heavy nucleus lead-2-8 using different many-body formalisms. So we have now obtained like a best fit interaction, and now we want to see how it performs. And the ones that were included in the fit was helium-4 and oxygen-16, as you see. We also calibrated this interaction on properties in calcium-48. And the other ones are predictions here. You can see quite well reproducing binding energies from light all the way up to heavy lead-2-8. For radii, we see a similar kind of quality. Again, highlighting those that were included in the fit, and the rest are predictions. And compared to data, which is were available, which are the black stars here. So you can see quite well reproducing both binding energies and radii. We are working on also computing spectra, and the first preliminary results, it seems to be of similar quality as the magic Hebler interaction. We also computed neutral matter and nuclear matter using this interaction here at different truncations level in couple clusters. You have no, there's no singles here because we are in a lattice with purely boundary conditions. So it's doubles in parentheses T, triples, and then the most sophisticated method we have implemented so far, thanks to Beiguang Jiang, he really took the lead on this, with what we call lambda CCDT parentheses T. So this really means that the turbidic triples are expanded around the CCD ground set solution. And you can see that the lambda triples corrections gives slightly less binding than what we had before, the CCD parentheses T approximation, and also compared to the empirical box, you can see that we are consistent with that as well. We also compare with other interactions. Here we have, this is taken from this paper by Francesco Marina, Beiguang, and Sam Navarro. It was a very nice paper they put out last year, where they used different many-body methods and interactions and did benchmarks, systematic study of various truncations. And just taking the results from there, from the different interactions here, you see the anti-low sats and also these delta GO interactions. They saturate at a bit higher density than the interactions that we just optimized.
Sorry. It's like, I remember and was also fit to reproduce oxygen-16 and helium-4, right?
Well,
What?
sort of, right?
Yeah, so what is
that's
the
why we
difference?
didn't have emulators, so we had to kind of just take snapshots in when we optimize and see how a particular set of legs performed in oxygen-16.
Okay, so, but it does reproduce oxygen-16, right? Both radii and binding energy.
Right.
The final number.
Right.
Why? So it doesn't reproduce oxygen-16, it reproduces helium-4. What is the difference with anterior load axis? Because it's N2 low at body, right?
Well,
That's
the N3LO, now we have N3LO in the two-body sector, while we keep
Oh, and arrows, okay.
the three-body force at
Okay.
same order.
So that makes the difference. So this, okay.
So we have 28 low energy constants.
Okay.
Versus with N2 SAT case, we had 16.
Okay.
So we have 12 more parameters to fit today.
Okay, thanks.
All right, so that finalizes.
What about other property, symmetry, energy,
Yeah,
compressibility?
I have results at the end.
Okay, I can wait.
Yeah, it's backup slide.
Yeah,
Okay.
we'll wait.
All right, so, okay, so let me come to the second part. So the very preliminary results and still running in the background. Motivation is there, of course, well, to study octuple deformations. You know that it's really important for calculations or the study of permanent EDMs here, right? And in the particular case of radium-225, there is this parity doublet, 1/2 plus and 1/2 minus, that is only 50 kV separation. And if you look at the shift moment, then you see that the transition here is really dominated by those two states. And also it has been observed that these radium isotopes here are octupole deformed, which enhances quite a bit these shift moments. So the goal is then to compute these kind of properties. Just to walk you through how we compute the deformed nuclei in copper cluster, right? So we start with a Hamiltonian, which is the intrinsic Hamiltonian with 2-body and 3-body forces. As many of you know, we do not include the 3-body forces fully because it's too computationally expensive. So we do this normal ordering approximation, right? So we neglect the residual, what we call here W3, and we keep only in a normal order 0-body, 1-body, 2-body piece of the 3-body force. We then typically perform a Hartree-Fock calculation, and for a spherical system like oxygen 22 here, for example, on the left-hand side, that will come out of the calculation. While if we look at the deformed system like neon 22, the Hartree-Fock solution informs us of those kind of breakings, emergent breaking of symmetries here. So really, in some sense, you can think about the Nielsen diagram on the right-hand side here as a guide or what the reference state for a given nucleus is, and what kind of or other prolate or oblate deformation. So one technical aspect here I would like to mention, right? So we do this normal ordering 2-body approximation. If you do the normal ordering with respect to a broken symmetry reference state, the resulting Hamiltonian will also not, in the case, will break rotational symmetry. So Michael Frosini and collaborators at Saclay came up with a very nice procedure how to deal with that. So they do first a spherical calculation, Hartree-Fock calculation, where there are fractional occupation of the last levels close to the Fermi level. And then they do normal ordering with respect to the spherical density, and you obtain then finally a normal order 2-body Hamiltonian that you back transform to the harmonic oscillator representation, for example, which is then the starting point for the subsequent deformed calculations. So we follow the same procedure. We first perform a spherical Hartree-Fock, do this procedure here, and you can also see whether you use a spherical harmonic oscillator, HFB, GCM, or HFB reference here to do this procedure. In particular for these nuclei here, the dependence is quite weak. There's a problem if you go very deformed, of course, because you don't really know what the level structure is close to the Fermi surface and what the fractional occupation should be for those orbitals. So that's a challenge that we are thinking about and how to solve, or especially for heavy nuclei and strongly deformed systems. So the procedure is the following. So we include what we call short-range correlations, where the standard couple cluster calculations, where we act over e to the t operator on our broken symmetry reference state here, Hartree-Fock solution. And then we include what we call long-range correlation via symmetry projections. And we do that typically with what we call projection after radiation. So we have our couple cluster right and left state. And now that we also break parity, we have to project back on both angular momentum and parity to obtain states with good J and parity. Typically, this amount here that you get from projection here, which we call small delta E here, is very small compared to the correlation energy you get from including the short range correlations via the acting of e to the t on your reference state. You also see that in a picture here. This is the binding energy of neon 20 computed with triples excitations, and you see the binding of 156 MeV here, while the projection gives you only a couple of MeV additional binding. So small quantities that if you're looking at total binding energies, but they are very important if you want to look at rotational structure and excitations and also transitions within those rotational bands, of course. So now coming to the new stuff here, we want to do constrained couple cluster, kind of inspired by what Michael Frassini and collaborators did here within the PGCM approach, or this is called Hartree-Fock-Bogoliubov case here. So they do a scan of beta 2 and beta 3, which are related to the quadrupole and octupole moment, mass moments. And they found that in potential energy surface, where the minimum here for neon 20 has 0 octupole deformation, but is, as we know, quadrupole deformed. But then, as you see, there is this trajectory here. If they vary beta 3, there is a minimum or valley where the beta 2 optimal value is. So inspired by this, we solve the constraint following problem. We have a normal order two-body Hamiltonian with dipole and octupole constraints. The reason we need to include the dipole here is, as we go, we want to fix the average position of the center of mass. So we constrain the dipole moment to 0, while we vary lambda 3 that enters the octupole deformation here to scan, or basically to scan this valley here in couple cluster. So the energy functional that we need to minimize or is given here, and the stationary solution implies that the variation of this energy function here with respect to the t amplitudes and the left lambda amplitudes for the left ground state should be 0, and those equations leads to the standard couple cluster calculations. Okay, so we will do now CCSD. And then we solve these equations under the I'll figure this out, under the condition that these constraints are fulfilled, right? And then once we do that, we can also finally perform projection onto good parity and angular momentum as well to get the positive and negative parity bands. All right, so this is showing you now the constraint couple cluster results for neon 20 in a small model space. So this was just performed this week, so that's to quickly do this. But these are extremely expensive calculations. So every point here, so now we vary Q30, we constrain Q10 for each of these points to 0, and we fall in this valley where the beta 2 is optimal. And so the blue ones here are the unconstrained, unprojected results. Each of these points requires typically about 1,000 couple cluster singles or doubles function calls. Because for every update to t, you have to solve for the left ground state solution lambda, which has the same numerical cost as a single call to the t amplitudes. So then you can just imagine what the cost is here for each of these points. And after that, of course, also doing the projection back onto good parity and angular momentum is an additional order of magnitude increase in the cost compared to the unprojected calculations. So obviously here, emulators would be very useful to decrease this kind of very expensive calculations. And again, we see that the Hamiltonian here depends linearly on these lambda 1 and lambda 3 parameters. So one might think then, of course, that we can apply here in this case as well the eigenvector continuation technique and subspace couple cluster theory. So that's what we did. We chose a set of lambda 1 and lambda 3 for which the first few points here, or those are the training points. And then we want to predict the rest of the curve and also the projected minimum for here the 0+ state, for example. So basically then we have our set of training points or training vectors, the right solutions and the left couple cluster solutions. We project then all these operators here, two-body Hamiltonian, the electric multiple operators, and also the parity and angular momentum projected Hamiltonian onto the subspace of snapshots. We then perform a nonlinear least squared problem, optimization problem in this subspace to determine lambda 1 and lambda 3, for which Q10, the dipole is 0, and also we have specific target value for what the octopole deformation should be. This is the result. So now we have 6 training points. The red diamonds here are the exact calculations, constrained couple cluster calculations. And the green line is the subspace couple cluster prediction for the unprojected constrained couple cluster calculations here. So you see in this whole range for Q30, we get a pretty good agreement with exact. And if you also include more points, so this is 6 points, if you go to 8 points, we basically lie on top of the exact calculations. These are now showing the projected 0 plus, 2 plus, and 4 plus state as a function of the octopole deformation here. Again, now we have 6 training points. The diamonds are the exact calculations, and the solid lines are subspace couple cluster predictions. And you can see, it's difficult to see, but there is a minimum around here. It's very flat, but this is for the 0 plus projected state. So it is, you see, it's soft towards being octopole deformed and not a clear minimum, but also to take into account that this is a very small model space here. So this will change as we increase the model space. Go from 6 to 8 training points. You can see that we improve the predictive capabilities of these emulators here, and now basically following it all the way up to here. So octopole deformation. And we can also do the negative parity band. So this is the 1 minus, 3 minus, 5 minus states in Neon 20. Again, as a function of octopole deformation. Here, there is a minimum around here, and also the rotational band that we get for the negative parity band. I didn't show it here, but it agrees pretty well with experimental, also the experiment for these states, also for the 0 plus rotational band. And that's all I have. So I'll just leave this up there, and thank you all for your attention.
Very impressive results. Really nice. Are there questions? Yeah. Sean.
That's, the typical question I learned to ask, you did this for a specific H bar omega and stuff. Does it kind of extrapolate to other H bar omegas in the reasonable range? What you just showed.
It extrapolates.
Well, you did 16.
Right.
If you do like 14, 20 and stuff, no unreasonable H bar omega.
Well, things will depend on those parameters. In particular, it's so small model space that we do. But eventually, you would see as you go large enough in Nmax that
Then it should not depend anymore.
these curves of potential energy surfaces should not depend on your basis parameters.
In principle. And then I saw you had, when you went out very far, the prediction,
Right.
Is that just also an artifact of the size of the model space or an artifact of the extrapolation? That one.
You mean what happens here?
Yeah.
I would think this is an artifact because of the small model space that we have. But okay, we'll see. But the physical minimum is around here. So this is.
So you actually don't even care about that?
No, I would say this is a basis truncation problem. But yeah, you see it turns down again. So this could also be related to, we do this normal ordering of the 3-body force, right? So you see that in heavy nuclear as well. You go to very, very largely, very large deformations. The 3-body force does not capture the kind of repulsive bonuses needed to stabilize these curves. So we fall off a cliff there too, right? So if you go to very large deformation, I think things are not well under control yet.
I shoot one more question since you did Neon 20. And I did a reaction with Peter Barris's Neon 20 on Christina's Neon 20. Neon 20 is deformed and is clusterized. Did you look at another observable like the RMS or something and not only at the energy? How does that behave?
Not yet, but all of those things we can do as well.
I was just curious because
subspace
Christina
of-
has difficulty to get the RMS.
No, I mean, once we have these, we can project any operator onto that subspace. very
Okay.
easily, right?
So it will come.
Yes, it will come.
So, two questions on the nuclear neutron matter. First,
Oh,
first, the question from Dick.
that's true. Yeah, I forgot about that. Here's the answer. Right, so here the red star is this new interaction, right? So comparing to work that we did with this that 2.8 paper, history matching, and also work with Wei-Guang Jiang, we will develop emulators for nuclear matter. So this is the empirical box, right? So we have symmetry energy, energy per nucleon, density, striation density. And you can see that the new one is consistent with the empirical box for most of the years. Quantities.
Can you say something about what part of the Hamiltonian is providing saturation in nuclear matter?
Not there yet. But it looks like that in this optimization here, the three-body force is the critical part, and in particular the CD component. So when we start, it tends to drive the CD to kind of large values. That seems to impact both saturation density and also radius in oxygen 60. So it favors large values for the value of the CD. So that seems to be one of the most important.
Including the radius is critical, right? Oxygen 60, otherwise you don't get saturation.
Right.
So then I'll follow up one more question that there's this connection between CD and EK matrix elements.
That's a good question, and we haven't looked at it, so it might very well be, you know, either we get the beta decay right or the radius right. I don't know. We have not looked at it yet.
Interesting to see.
Okay. Can I ask a really stupid question? What is the box? What is the box?
Well, that's the empirical box. That's where does it come from? I don't know.
Sort of a consensus of the community
Yeah.
based on experimental
Okay.
data, theoretical. Certainly shouldn't be a box. Yeah. Other questions?
For the deformation, but you showed that it's not so obvious you have a minima. But it's, you said that there's a minima of the Q30.
Right.
About that. So do you think you can explore more to, for example, to increase the three-body force a little bit, or increase some p-channel interaction a little bit, then you can have a deeper minima.
Can increase the, sorry.
Increase your some part of your interaction of your current interaction. For
Yeah,
example, increase your three-body force, and then probably you can have a more deeper or more stable deformation or something.
I could imagine that, because now we have the three-body force is truncated at E3 max of 16. Right, and as we go to larger deformations, I think that might not be sufficient. And also the Nmax here for the single particle basis is only 6 major shells, which is quite a full space with it. So I think the picture here is just preliminary, but and it will change as we increase the bond space.
So you believe that three-body force definitely played a very important role for the deformation, right?
Yes. Please.
And also my body contact is most impactful
Okay, this is your talk, so. I mean, I'm talking about how these curves look at the limit. That's one large deformation that is impacted by the 3.8 force, how we handle it.
All right, let's thank Gaute once again.
Yeah, I just I've already downloaded it. This is for information. Yeah. Try to change the light because how it works.
Great. Okay, so we've saved our best talk for last. Thomas Papenbrock from UTK and Oak Ridge will talk about emulators, tell us about nuclear deformation and Hartree-Fock mass models.
Thank you, but I doubt that, Dean. And I know I stand between lunch and driving away, so I'm conscious about that. So this is a picture that I want to explain in this talk. So what we learned is really, or what we believe is that how do you look about deformation is, of course, like many other things, a very resolution scale dependent thing. Okay, so I also have two papers I want to present aspects of two papers. The first one Gaute already mentioned and somehow had its lead on this, right? And the second one just came out last night, just in time for the quarterly report. We're very happy about it. That was led by Chinmay Mishra, who's now at Livermore, and it's about a nuclear mass model rooted in chiral EFT. And I want to talk about the technical aspects. In both cases, we use Hartree-Fock emulators. So, if you think about Hartree-Fock emulators, you would immediately say, well, that seems like a tricky business, because somehow you have a matrix. Hartree-Fock solutions are Slater determinants, but of course, if you superpose Slater determinants, these are not anymore Slater determinants. So you have to make sure that you don't get a GCM or generator coordinate solution, but rather the solution of a one-body Hamiltonian. Yeah, so that's just what I like to say somewhere up here. Yeah, so how do we do this? Of course, we have a Hamiltonian that depends on linearly on some coupling constants, low energy constants. We call them here xi. Yeah, and now the key is, of course, we have also a Hartree-Fock Hamiltonian, and very important, the Hartree-Fock Hamiltonian, of course, is technically a one-body Hamiltonian. Has been determined self-consistently, but it's a one-body Hamiltonian. And of course, every one-body Hamiltonian has a Slater determinant as its ground state. So that will be the key. Yeah. And so in a reduced basis, yes, we have a Hamiltonian matrix and a norm matrix. But now the key step is really, what does it mean to apply this reduced basis to a state psi? Well, we take the matrices of this reduced basis at this point, then we have a one-body Hamiltonian, and we keep the freedom here, not inside here, but rather only out here. And so in that sense, we linearize a non-linear problem, if you think about that. And then, of course, at the training points, the Slater determinant will be exact the solution, and in between, you will always have the Slater determinant as a solution because this guy here is a one-body Hamiltonian. Yeah, so I just wanted to make this point. We do not want to just naive Ike vector continuation. Would you give something that is better than your Hartree-Fock solution? Yeah, we went down this trip and we coded up first, then we learned how to do it right. This is how to do it.
So that was interesting. So you're basically doing again vector continuation on the single particle orbitals.
That's why on a single particle Hamiltonian that has been
defined.
Okay, that's why. Absolutely.
Yeah, but that would turn into doing again vector continuation on the single particle orbitals. That when you assemble them, you have a single Slater determinant anyway.
That's right. That's right. Okay, and yes, I like to say this. We do Hartree-Fock. Yeah. If you have not seen this movie, your parents sheltered you. Yeah. Good. So now the first thing is, so we want to build a nuclear mass model. Oh, yes, please. To the movie.
It's not just about single particle ground state, right? It's actually about the whole spectrum, like ground state, excited states. You feel the levels.
But yes, but we here care only about the single particle ground state. Yeah, so of course, the Hartree-Fock Hamiltonian has also excited state as well. They are also more magnetic permanents, but we don't care about that. Oh, I'm
He
misunderstanding.
doesn't care about it.
I can ask you later.
Misunderstood your question there.
Yeah, that's exactly the point. I am confused, but I can ask you later.
So we want to do an approximation. We just look, we want to know what is the ground state for a Hartree-Fock Hamiltonian. Okay. So the idea came, so we want to build a nuclear mass model with some roots in QCD. And of course, there's long effort in the community here, more than a decade old, a long list of names. Dick is here and many other people who have been interested in that maybe as a good. So motivation for this work is simply a few years ago here in 2022, we thought about how would one renormalize coupled cluster theory. So we have 2 particle, 2 hole, 3 particle, 3 hole correlations. And the idea is simply, well, yeah, short range, for instance, 3 particle, 3 hole correlations, of course, yield extensive contributions, so proportional to mass number, to the ground state energy. But this is, of course, so it's a 3-body thing, it's a correlation. If you want to integrate that out, you would have to, a la Lepage, you would have to renormalize your Hamiltonian. In that sense, change your 3-body contact. Yeah, so that's just Lepage applied to coupled cluster theory. And this slide here on the right-hand side really shows you can actually do this. This works. Yeah. So here on the set of nuclei, on the left-hand side, you just see an energy budget, black Hartree-Fock contribution. This is whatever color it is, coupled cluster, doubles, singles and doubles. And then this small orange sliver, AUT, is from 3 particles, 3 holes. Yeah? And now we renormalized this 3-body force, so this contact, just in oxygen 16, and demanded that basically double CCSD gives the same result as the full triples calculations. And that's here what you see here in oxygen 16. And now, basically, most of it has been shifted into Hartree-Fock here, and that's it. Yeah, and then we can compute other nuclei, and you see here the budget is always very similar. It sort of works. You can integrate out triples by renormalizing the 3-body contact. Okay, so now if that is working, you might just be extreme and pushing this to extreme and say, okay, can we integrate out 2 particle 2 hole correlations and just solve Hartree-Fock and then be happy? Yeah, so this is by now the idea. So we renormalize all contacts, all short-range contacts, and then this would make Hartree-Fock or maybe better GCM, but only long-range physics would be needed to get a solution. That's the idea. Get a mass model based on Hartree-Fock with roots in QCD because we would start from chiral interactions. Okay, so we did this now. We constructed. I've shown you how we construct emulators. We know how to construct emulators for Hartree-Fock. And now, okay, I'm sorry, let me go back. If you want to do this, you have to adjust a large number, or order 10 or so, low energy constants. So then even, right, just a Hartree-Fock calculation with 3-body force is too expensive. So that's why we need to build emulators. So, okay, so the idea now is, right, we started from this delta analog go interaction, and the idea is just to adjust all low energy constants so that Hartree-Fock gives an accurate ground state energy. So yeah, I just said it, we need to do this. So we want to calibrate a mass model and make predictions for mass models. And so here, just simply here, these are the low energy constants for the experts in the room that we have to adjust here. Yeah, and but we still do a few simplifications here. The first simplification is here. We decide that our Hartree-Fock state is spherically symmetric or axially symmetric. So no triaxiality or things like that. Yeah. And that I think is a good approximation. Triaxiality has a very small impact on binding energy or ground state energies, it seems. At least much smaller than the accuracy we will be working at. But then we make a more crucial decision. We also say we only consider prolate shapes. We don't want to have one Hartree-Fock model for oblate deformation and one for prolate. Keep it simple. That might not be always accurate, but this is just what we do. And then in the end, this interaction has more than 11 contacts, but we don't distinguish much between protons and neutrons here in this channel and just leave it isospin symmetric. We wanted to have it a little bit more simple. Yeah. Good. So now we construct emulators, and maybe let us just start here on the right-hand side here. This is a validation picture. It's really the magnitude of the relative error in percent. So this is not a good wording. It's a magnitude of relative error in the preprint today is a better wording. This is for calcium 52. So we vary here all these 11 constants and dice out things, and then we let our emulator do its business. We make a exact Hartree-Fock calculation and compare, and you see here's a difference. Yeah, and you see also here this is the energy of chromium 452. So this is where we want to be, and you see, okay, we are of the order of 1% or better. We wish we were a little bit better, right? 1% of 500 is still 5 MeV, but that's where we are. And then, so we were first a little bit disappointed that our emulator did not work better, but then we looked back at something else we did years ago, Octane 16, with a different interaction. And if you take the same ratio here, and you just vary one coupling coefficient, it's just CE, not 11 like here, yeah, you get a little bit better than, but 0.1% or so is maybe a better CE. Yeah. But it's not completely out of the question.
Right figure, how many training snapshots do you?
About 60 or so. So we have 60 to 100. Yeah, we have 11 constant, but that's about it. We use this hyper Latin lattice again and do our things there. Good. So now then we have to calibrate our mass model. Yeah, so we have emulators. We created emulators for all of these nuclei, and this is the set of nuclei we just used, right? So from oxygen 16 here to nickel 56. So to do what we would do. And then here's again just plotted the energy budget. Black is experiment. So what we really would like to have. Blue is now what our Hartree-Fock calculation gives us. And just for comparison, if you just take the delta Go interaction and just do Hartree-Fock, you get about half the energy, right? So of course you miss the correlation energy, but this now we renormalized. Okay. So this looks good, but of course this is binding energy per particle. That's why it looks so good. Good. So here's a little bit, the right plot again. So here, these are the original coupling constants of this interaction. And this is here how the renormalization goes. Here, you see this better even here. We made them dimensionless here, follow Dick and others' works. But you see here, the main renormalization happens in the three-body sector. Now that's where all the juice is. The other things are really small. We just made this plot we wanted to, so these three-body constant, I would say, were unnaturally small to begin with for this interaction. So now they are still something like what we would call natural, yeah? And all the other constants are as natural or unnatural as they ever were, yeah? So here, this here was always a little bit large, but we didn't change that.
Yes, at this point, I mean, what happens if you just change CE and CD and leave everything else unchanged? How much worse would that be?
We do not know because we didn't try that.
The best values would be slightly different from the one that you have now, because now you're optimizing everything.
Right.
So
and that's even is more. So basically, when we I have more to say this here. So you see CD here. Minus 2.0000, so very suspicious, yeah. And it is because it is at the limit. So we set an emulator, and when we made our emulators, we said we make a trust region where we optimize. And because right, the central value was so close to 0, we thought, okay, if it's larger than magnitude of 2, this is not where we want to go. So we don't trust our emulators too far out there. So there could be a point, right, CD 6, 7 or so, that would be better, but we do not know about it. So this is a constrained optimization where we did not want coupling constant to run too far out of a window that we trusted. Yes.
So I'm not intimately familiar with your minimizer that you use, but there's no validation set here, right? It's just you have the data, you fit to all of the data.
That's right. We fit to. That's why That's absolutely right. The validation comes basically in the next slide, when we now let this loose, this mass model loose on other nuclei.
But there are fewer parameters that fit together, right?
We have 11 parameters and a little bit larger, 19 nuclei or something like that. Yeah. Great. So now mass model prediction. So now here, you see here, this is a plot in the NZ plane of differences between so we now did Hartree-Fock calculations with this new mass model and difference to experiment. The circles here are all the nuclei that we used in the calibration, and squares are in that sense prediction, validation, yeah. And so this is how it does. We land at 3.5 MeV root mean square error. Here do I have this here? Right. So on this training set or in this optimization set, we have just 2 MeV root mean square error. Yeah. 2.17 or so, but then it goes, if we let it loose on the set of 100 nuclei here, it gets larger. And here's also as a function of Newton number, all the isotopic chains we have. And so here's the outliers here, right? So maybe not too surprising, these are nuclei that are spherical but very soft. And of course, we don't capture them there. We make them deformed where they are also the Silicon 28, right? B5 half filled for the local experts here, yeah, and sulfur is not much better. So these are, yeah, so we probably, yeah, we have ideas how to get this better, but it's clear the Hartree-Fock state alone as a single product state will not do very well for these. Okay, so improvements, possible improvements. We are seeking, right? We are seeking things of the order of 1 MeV or couple MeV, and there are many things that come to mind. Of course, we should distinguish between oblate and polate shapes. We should do angular protection. Maybe we should include pairing. And then also for things like Silicon 28, full GCM. That would give us a little bit, these are all contributions of the scale of an MeV. That's essentially where we are. Okay. And that's the first story. Second story, and I will be brief here. What drives nuclear deformation? This has been evolving view in time, yeah, and starting in the 1950s, yeah. So a small snapshot on history here, right? Nielsen model, yay, yeah. Just a deformed well plus an LS coupling plus an L square term gives you things, or Elliott would say quadrupole interaction. And what is read here always on the slide is it's this long range forces. Of course, we don't have that in chiral EFT, but that would give it. Then in 1960s, Hartree-Fock calculations used pairing plus quadrupole Hamiltonians in a single shell and explains this as a competition between pairing and quadrupole. Element Pitel, yeah, I read it off here. Deformation sets in when certain interaction matrix elements here dominate over pairing. So again, this competition, Hick looked at this in relativistic mean field models and found that deformation is very strongly correlated with nucleon effective mass and with spin orbit strengths. And then finally, the shell model folks, Strasbourg group would say the monopole proposes multipole, so that's multipole proposes, monopole pairing disposes. Good. Good. So now we can ask, how does this work in chiral EFT? And I go forward here. So now we are ready to answer this question, and we answer it again. We do just Hartree-Fock calculation, projected Hartree-Fock calculation, like Gaute showed also in his slides. Yeah. So we use a simple ratio, the so-called R42 ratio. Yeah. So that's the energy ratio of the excited 4+ state over the 2+ state in even nuclei. And if you have a rigid rotor, if this thing would rotate, you get J times J plus 1, you get a ratio of 10/3. And for spherical nuclei, you get more an harmonic spectrum. And you see this is here from NNDC, color-coded, the R42 ratio shown here in the rare earth region. And then you can also look at the beta-2 as a deformation. This is really also not observable, but the BE2 transition strength is an observable, and this is a formula that people use. And you see just here deformation here, just the colors match, is related to this ratio. So we just look at this ratio. Good. And then this is so our executive summary, our highlight. What are the main effects? What are the main low energy coefficients in chiral interactions that correlate with the R42 ratio? And it is S-wave context. It's short range physics. That's why I had to say, well, you see three nucleon forces, not really on deformation, of course, on saturation and things like that, but for deformation, it's very small, but the S-wave context is really the driving force here. Ion exchange just a little bit. And this is a more detailed view again here. Yeah, you see here, it's short range physics that drives it here. Particularly here, right? This is the next to leading order singlet S guy. Yeah, good. Okay. Summary. I would say our technical advance has been we have developed Hardy-Fock emulators. Yeah. And then the science results is we have a Hardy-Fock model now with mass model with roots in chiral EFT. And we found that the nuclear formation is most sensitive to the singlet S contact at next to leading. Thank you.
Are there questions?
Yeah, I mean, it's okay. If I remember what I learned about, were you surprised that P rates don't contribute more to formation? I saw your figure. I'm impressed, but
did not know what to think really, right? So yeah, we did not know, but we were happy that the picture is simple. Right, so
I mean, naively, I would have expected there is some momentum driving deformation, and you said no.
I think this is really the shell model is a nice, but often also very complicated tool to look at deformed nuclei.
Definitely interesting.
Very nice result. So you go back through the slide which you show the contribution. Yeah, this one. So
this one. Oh, I'm sorry. This one.
Yeah, this one. Do you think that is a global behavior of all the nuclei or only those three? Because for different nucleus, if the nucleus occupy different positions based on in momentum space strings, if we look at the phase shape, they have the different strings for the different channels, so that could make some difference, right?
Right. So we told this only for these nuclei. So and out of these nuclei, neon 32 and magnesium 34 are fantastic rigid rotors. Yeah. So if you look at the spectra are known, it's wonderful J times J plus 1. Yeah. Neon 20 is not as rigid. So that sense, this was an ensemble of nuclei, this mass region where we at the moment think we can do business well. And they at home. Yeah, we wished we could do this for rare earth nuclei, but not yet. So so I would say it could be, but then I think let me go back here. Is the statement here has also been done just in PF shell and at D shell nuclei. Yeah, so it could. Never mind.
I wonder if you can, of course, you're looking at a very broad range of things, but how many of these nuclei are very clustered? Lots of alpha cluster structure, for example. I mean, I think of that as also being a source of deformation and very sensitive to S-wave contact.
Right. So, of course, so we do not have 4 particle 4-hole excitation. So in that sense, with the alpha clusters, we have no non-trivial alpha clusters. We have alpha clusters in the sense that we have shell model orbitals that could be, of course, 4-fold the reference state. That's as so we have not more. Then also there was this Nature paper 1 or 2 years ago by the folks who TIN 100 or so said there would be a lot of alpha clustering describing. Yeah, I don't know.
On the first part of the talk. So naively, when
I'm thinking of going from a realistic Hamiltonian to a Hartree-Fock, high solution Hamiltonian to Hartree-Fock Hamiltonian. And a way of thinking about it is with a unitary transformation, I would say, and then I would soften it a lot, then Hartree-Fock would be the solution. In that case, I'm not surprised that you have strong three-body force in a sense because of the induced three-body interactions. But then I was thinking, what if you included a four-body contact? Is it very hard technically to do or not?
For us, yeah.
Even at the Hartree-Fock level, I mean, that's what I mean. Because you need that term only at the Hartree-Fock, like as an induced.
Okay, so, okay, at the moment, how we do business, the answer would be yes, because we always start from matrix element at the oscillator basis. But of course, if I think about it as a density dependency,
Yeah.
then maybe not. But yeah,
Just, as a subleading term that you might need to fully normalize. I mean,
raise a good point. Yeah.
With this Hartree-Fock mass model, have you looked at heavier nuclei?
No. And this comes also just because what Gaute mentioned, this normal ordering that we do, this normal ordering approximation, is also the basis of these calculations. Mass heavier than 80 or so, this becomes questionable. So we left it where we thought that would not be impacting our results here.
Questions? What do the single particle states look like? I mean, single particle energies and stuff. Which for your Hartree-Fock, just any of them. So I'm just looking, what they just look.
Oh, Mike, no, good question. I have never looked at it. So no, it's in the data. So we have.
Yeah, sure.
Yes, we can look at it. We have not. So but not from these calculations, not from the renormalized calculation, but when we start always from reference Hartree-Fock calculations. Fock spectra. We discover the Nielsen diagram every day. Yes.
I guess back to my question, how is there the strength of the S-wave contact, I would think, would also depend upon what cutoffs you're choosing for pion exchange, in a sense, compensating each other.
So all these results were for this soft interaction with about 400 MeV, 394 MeV cutoff. Yeah, so it is a resolution scale dependent answer to question, and we just looked at it at the resolution scale of one chiral EFT.
Yeah, I'm just thinking your S-wave contact might be kind of broad and not really a contact.
No, yes, absolutely. Right. Yesterday, 1.5 hectometer, well, is a very good number, very good number.
I'm thinking that if we apply our interaction, we will get the same deformation, even without pions, very soft. And, because if that's the one that dominates it, then we have it.
That's fine, that's fine, that's fine. That's fine.
Questions? What about nuclear matter?
You mean with Hartree-Fock emulators? No, we could do it. Yeah, so no doubt, but for nuclear matter, we use always a momentum space, a cubic lattice in momentum space. And here we use an Hammond oscillator basis. So it's not just changing mass number and getting nuclear matter. It's a different thing, but no doubt one could develop it.
Let's thank Thomas once again. Have actually reached the end of our program. So that's all the talks that were all wonderful on the second day as well as the first day. And thank you everybody for the great contributions you've made to science. Hopefully we can be funded with the next circle. And but before we close, maybe mention, so Bob told me that at the guest house, there is a special, Bob, is it?
Yeah, it's on Wednesdays and Thursdays, they do a special, it's a little more expensive than cafeteria and a lot better. And today it's Cinco de Mayo, chips, salsa, guacamole, shrimp quesadilla, chicken tortilla soup, cheese enchiladas, Tijuana Caesar salad, and beverage. They give you like lemonade or iced tea. And it's usually about $16. So it's one or two main things and then lots of sides, which are unlimited.
Okay, so that's definitely an option. Anything else?
No, so the only spot available is at 3 p.m. So if you want to stay, that's fine. Otherwise, that's for free. We cannot do that earlier. Yeah. Just let me know.
Yeah, was there anything else you mentioned?
Well, no, I mean, thank you for coming. It was great to have you here. I hope you liked the pizza yesterday for those who came. And what else? Well, I'm looking forward to see you again soon, hopefully.
Thank you.
That's it. Yeah. Yep.
Thank you, Dean, for sharing everything.
Sure.
Yes.
Sure.
Yeah.
Okay. Thank you, everybody online for tuning in. Have a great rest of your day, and to everybody that's driving, flying, safe travels, don't hit any deer, and
Oh, and guys, room reserved until the end of the day, so if you know.
But I still have to go home.
I have a way to explain this.